We're going to take a very brief look at carbon and a little bit about organic chemistry. So carbon's our building block of life. Organic chemistry studies carbon and its compounds. Tons and tons and tons and tons and tons of carbon compounds. Why? Because carbon bonds in a lot of different ways. Carbon can do 4 single bonds, a couple of double bonds, a double bond and a couple of single bonds, a triple bond and a single bond. There's a lot going on with carbon. So super, super, super important. All right, now when we represent molecules, we can do a lot to have different methods of representation. We can do structural formulas, we can do these ball and stick formulas, we can do space filling models. When we look at this, we can also do some structural drawings. So we have these structural formulas, and then we have these line angle drawings. The nice thing about the structural drawings versus the line angle drawings, we get really tired of writing all of those hydrogens out. So in a line angle drawing, every end and bend represents a carbon with the maximum number of hydrogens around it. So carbon likes 4 bonds, 4. It doesn't like 3, it doesn't like 2, it doesn't like 1. So if I look at something like that first one, that N-butane, so I have 2 bends and 2 ends, so I have a total of 4 carbons. Okay, at the end, that carbon is bonded to one other carbon. So the end carbon needs 3 hydrogens around it to make 4 bonds. Okay? Our bend carbons need 2 hydrogens around them to make our 4 bonds because our bend carbon is bonded to a carbon down here and a carbon over here. And so at that bend there, it's got 2 bonds to it, so then it needs 1 hydrogen and another hydrogen. So you can look at each end and bend, figure out the number of carbons, and then add in as many hydrogens as you need to get to 4 bonds. All right, and so we can look at benzene. So benzene, we've got the cyclic structure. There's 2 different ways we can draw it with the double bonds. And so if I have, that carbon there at the top, and I have a single bond over here and a double bond over here, that's 3 total bonds. So to make a 4th bond, I need 1 hydrogen. And you can see that depicted right underneath where each one of those carbons has a single hydrogen on it. All right, and then we have all of these functional groups. These functional groups do a variety of different things that give us some very interesting physical and chemical properties. And so having a functional group present in a molecule and where the functional group is responsible for how a lot of our drugs work. And so we get, you can see going down the line, we've got alcohol. So then I have ethanol or ethyl alcohol. You can see it has that OH on the end. Or ether, I've got a carbon, an oxygen in the center out to another carbon. So an example there is that dimethyl ether. So you can see the carbon, then the oxygen, the carbon. So you can see that in there we've got these functional groups highlighted in red. Aldehydes, we've got a carbon double bonded to an oxygen and then bonded to a hydrogen. A ketone has a carbon, 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 where the middle carbon has a double bond to an oxygen. Carboxylic acids, the COOH. Acetic acid is a carboxylic acid. So you've got a carbon that's double bonded to an oxygen and that's bonded to another oxygen that then has a hydrogen on it. The hydrogen on the end of that COOH structure, that's the acidic hydrogen that dissociates in a carboxylic acid. Carboxylic acids are really common weak acids. We have esters, amines, amides, and so we have all sorts of these functional groups all over the place. So here's an example of where some functional groups are. You can see this thyroxine, it's a hormone precursor. So you can see circled in green there, we have an amine group. Circled in red, there's that carboxylic acid group. Circled in blue, you've got that ether group. And circled in purple is an alcohol. All right, so all sorts of functional groups all over the place. Then we have something called isomerism, where I have 2 things with the same formula, but different properties. So we can get structural isomers where things are bonded differently, and stereoisomers where things are bonded the same, but we have different spatial arrangements. So we can get subtypes there. So we get geometric isomerism, so cis and trans. So cis are where things are on the same side, and trans are where things are on opposite sides. And then optical isomers, these are really interesting. Your hands, we're going to look at this again in a minute. Your hands are optical isomers, okay? They're mirror images of each other. but they're non-superimposable. If I orient my hands the exact same way, they're non-superimposable, only the mirror images, okay? So our geometric isomers, so this is a cis and a trans compound. So you can look at the two structures I have there. Look at the yellow balls, okay? So my cis, I've got them pointed the same way. My trans, they are pointed opposite from each other. And so you can see one of them is this kind of dark purple color, the other one's green. And all it is just a difference of where two of those things are located. Okay, geometric isomers. Okay, so here, again, cis and trans. So here you can see the two greens are on the same side. The other one, you can see the two greens are on opposite sides for the trans. So this is cisplatin, okay? So cisplatin, the cis isomer, is an anti-tumor agent. The trans isomer does nothing. It binds completely differently. It doesn't fit in the same spot that the cis isomer does. Okay, and then we get this optical isomerism. So that's where we look at our hands. So what happens is we get these stereoisomers. They have the same arrangement, different orientations. So optical isomers, mirror images, okay, that can't be superimposed on each other. So we have to get asymmetry to get optical isomerism. If we have this asymmetry, we call it a chiral molecule. And so if we have a carbon that is bonded to 4 different groups, we have a chiral center. So you can see here I've got optical isomers of 3-methylhexane and alanine. So alanine is one of our amino acids. Okay, and so we have chiral centers on both of those. So you can see they are mirror images of each other, but they're non-superimposable on top of each other. Okay, and so again, your hands, okay, your hands, non-superimposable mirror images. We call these enantiomers. Okay, organic chemistry in college, as you're trying to learn this chirality and everything, you can see the first time you test on this stuff, sea of undergraduates in a lecture hall all sitting there like with their hands going, wait, okay, if this is this atom and this is this atom and this is atom, is this chiral? Is not this? So it's pretty funny, that, you know, because our hands are such good examples of that. All right, and so you can see here where if we have an enzyme that has a specific shape that we can bind to, like a lock and key, all right? So you know if you take a key and you try to put it into a lock that it doesn't fit, it's either not going to go in, or if it does go in, it's not going to turn. So this is what's happening here. If you have something that's trying to attach to a binding site where it doesn't fit, it's just not going to fit. But if you have something that does attach to this binding site, it's going to lock in very nicely, and it's going to do what it's supposed to do. Okay, so a lot of drugs, it's when you, synthesis is really crazy. When you're trying to synthesize something, if you end up synthesizing stuff in a mixture of 2 chiral molecules, it's very hard a lot of times to separate them. And so a lot of times what you'll end up with is you will end up with what we call a racemic mixture of both the active one and the non-active one. So a lot of drugs are chiral. Most of the time, the active one does its thing, the non-active one does nothing. Ritalin, it synthesizes in this kind of a mixture. One version's active, the other one's not. And so, you know, part of it just does nothing, just sits around in your body, doesn't bind to anything, doesn't cause any harm. Other times, though, we find out that that other isomer causes harm and does things we don't want it to. There was a diet drug a long time ago that when I was a kid, it was called fen-phen, and it synthesized like this. Did a great job. Lots of people lost weight. Super miracle drug until people died. What they found out is that the other isomer of fen-phen that they could not reliably completely separate bound to another site in the body and killed people. And because there was no way to guarantee 100% separation, they had to pull it from the market, and it can never be used again, because if even 1% of the pill that somebody takes has the other isomer, it can kill them. So this can be a real problem and a real challenge when working on drug discovery. So when we have chirality, we have something where we have optical activity, so it'll rotate the plane of polarized light. And so we can get things that are D isomers and L isomers based on the direction that it rotates the light. So a D isomer is going to rotate it clockwise, and L isomer is going to rotate it counterclockwise. And so we're going to get, these physical properties, except they're going to rotate the plane in opposite directions. And so you can see here, this is what we mean by rotating the plane of light. In the body, we can tell enantiomers apart. They'll bind to different sites differently, or they'll bind to the same site differently and have different actions in our body. Okay, if we've got one where it binds properly, it might not do anything. If we have one where it, doesn't bind properly, again, it might not do anything, but it might do something. Most of the time it doesn't do anything, but every once in a while we get a situation where it does do something, and it does do something in a pretty gnarly bad way, because we obviously don't want to kill people. So this is, again, a real struggle with drug development and drug discovery.